want to get primed here too? This will be that side? Oh, my mic is on. Cool. When do we want to start? Should we wait for a few more people or just kick it off?
Yeah, hold on.
Okay. That's it. Yeah. Produce and consume. That's all we got. Testing 1, 2, 3. Sibilance. Sibilance. Where are the speakers? I see.
So there's another group living in the basement.
Okay.
Okay, you do that?
Oh boy. Don't want to let that happen. I'm going to claim a seat.
Yep, claim it now.
Probably next to you here. Behind you. Hello, everybody. Everyone sleep well, well rested, well fed, lots of pork products. All right. Because there's a bit of a mix here, I'm just going to ask for like a raise of hands. How many people are familiar with the concept of a tuple space, tuple space? Okay. How many people were familiar with the concept of a tuple space before they heard of RChain? Okay, only a handful. And how many people are familiar with the Special K project? Okay, so we can explain some of these things. All right, so the basic idea of a tuple space dates back to the 80s. There was a guy named Bruce Galertner who wrote a programming language called Linda, and he came up with this associated memory paradigm where he was basically pushing keys and values, like a key value store, into a sort of distributed repository, and that this was a way for many computers or many machines to communicate in network using this tuple space. And the idea like took off a bit. There was like Greg likes to talk about how there was a cottage industry of tuple space implementations in the 90s. I sort of think of it as in the sort of somewhat in the same sphere as the sort of utopian days of Smalltalk and Prolog and Lisp machines and things like that. But the idea hasn't really had so much traction in recent years. So then Greg in the mid-2000s was working on an embedding of some of the same ideas that you find in RowLang in Scala as like essentially an embedded domain-specific language in Scala. And that's what Special K is, but Special K also can be kind of seen as kind of a tuple space. And so in a tuple space, you would have this idea of like a key and a value, to put it in modern terms. And you would put data in at a key, same way you might do with like a key value store. And then you could also get values out of the tuple space using pattern matching. So it was like a sort of simplified sort of mechanism for doing queries. So as best as we know, Greg took this idea and added that you could store continuations in the tuple space, so that when concurrent processes were accessing the tuple space, not only could they get data back matching on these patterns, but they could also get back a continuation, which was basically the thing that they wanted to do once they had that data, the thing that they wanted to operate on that data with. So, are people familiar with the idea of like a continuation in broad terms? Okay, so it's just like a computational object representing like what to do next. So it could be something as simple as like a function, or it could be a more complicated coupling of a function and the surrounding environment, depending upon how one was going about doing it. So, all right. So yeah, Special K, it was sort of this embedding of RowLang type concepts into Scala. And as we were working on RChain, this sort of need arose to have something like this that was at the sort of core of the RowLang execution engine, as we call it, which right now is the RowLang interpreter. So we'll get into some of the details of that. But what we also wanted to be able to do was to provide a library for any Scala developer to use. And so that was one of the big design constraints when we came up with the current version, which I'm going to be showing today. So it's disk-backed, so that it's persistent. Obviously, this is very important in the blockchain space, but even in a pretty like casual sense, if we put a smart contract in our our computer crashes or the program crashes, we want to be able to pull up the node and be able to have the smart contract still be there and still be able to be run. So and then in the future, of course, supporting the blockchain and Casper, we need to be able to go back and deal with the sort of historical accesses to the store as well. So, when I came to the project about 3 months ago, there was a in-memory implementation of this that was written in RBL, the Rosette base language. I can sort of show you a bit of what that looked like. is the sort of top level here. Are people familiar with RBL at all? Show of hands. RBL. OK. Part of the story here is that RowLang, the initial implementation, compiles to a, well, it's a top to bottom, it's a compiler that compiles a Lisp-like language into bytecodes, and then there's a bytecode interpreter. It's an actor language. The syntax looks a little bit like Scheme or Common Lisp. We're not showing very much of that on this. You see pseudocode here, but this is like what the language is here. We're defining an actor called namespace. We're setting it up. We're going to put these things in, and then in another two files, there are definitions here for produce and consume. But those are essentially the two main verbs. We don't use put and get when we talk about this. We talk about this notion of producing and consuming. I'll show a little bit of that code just so you can get a taste for it. Let's do produce. So we'll give it a little more. So Kent deserves like a lot of credit, obviously, because he's writing in essentially what is a 25, 30-year-old language when he made this implementation here. But essentially what produce and consume are doing is they're going through the store and they are taking either pieces of data and they're looking for matching continuations, or they are taking continuations and looking for matching data. And we'll get into some of the specifics of that in a second. But I just wanted to give you a flavor of what the sort of initial implementation looked like. So, all right. So this is the Scala doc for the API of RSpace. So this guy is new. You can ignore him for now. We'll get back to him in a second. But these are the two main verbs right here, and I'll open those up one at a time. First thing we do, though, is we create an instance of the store by calling this create method. Now, how many people are Scala developers? Only a handful. I'll try to walk us through here. The idea here is that we have 4 type variables, one representing channels, one representing patterns, one representing data, and one representing continuations here. Okay, so in RSpace is parametric, we say, in these 4 types. And it means that anybody using this library can use their own types as channels, as patterns, as data, as continuations. There are a couple constraints on this. The constraints is that you have to be able to implement an instance of the serialized type class, which basically means that you can take your type and actually I'll just show you the code of this. It's actually a little easier to understand in the code. So if you have a channel or a pattern type or a data type or a continuation type, your type has to implement these 2 functions, encode and decode, right? And that's just taking your type and it's putting it into a byte array, or it's taking a byte array and it's parsing into your type. So for all 4 of those main types that we use, you need to implement this. But basically, the things that go into RSpace, from my perspective, are entirely opaque. So I have no real knowledge of the RowLang innards and the way that we deal with things in RSpace. It's just this sort of extensible API where you bring these instances with you and you tell me, this is how I want to serialize things. That's the first part. And then we have to have a way of pattern matching. I mentioned that before. So you have to be able to match between data and patterns. Which the IntelliJ mode was. So there's another type class called match. And match takes two things. It takes a type representing patterns and a type representing data. Damn, all right. And if you give me a P and you give me an A, you have to also have a function that like matches these two things together. And we don't just return a Boolean value. We don't just say there is a match. In fact, you can do something in the body of your match function to the data and then return a modified piece of that data. So we express that with an option. For those people unfamiliar with Scala or Haskell, an option is like either something or nothing, right? We express that in the type system. So if you were like a C programmer, you might have a null value, but here we do it a little differently. So, all right. So once you have written your instances for those two things, you have to have your serialized instances for continuations, patterns, data, channels, and your match instance for patterns, and then you can start to use RSpace. And so going back to the API docs for a second. We've got our two main functions. This is essentially where the rubber meets the proverbial road. So we'll start with produce. Okay, so you have your store in hand. You've done that create method that I showed briefly before. And you have a piece of data. And you basically want to associate that with a channel. So what we do is we search the store for continuation that may have patterns that match against that channel. And they match the given data here, this piece of data, against the given channel, right? I'm sorry, against the pattern at that channel. So if there is no match already in the store, if there's nothing like a continuation that's already in the store, then we store the data at the given channel. But if a match is found, we don't actually put the data into the store. So all we do is we then pull the continuation out of the store and we hand you back the continuation in the data you just gave us. So you can see here the return type is an option again, and there's a tuple of a continuation and a sequence of data. This sequence here is because we're not just handing you back the one piece of data you just gave us, but we're also handing back other potential matches, because when you're searching that store, there may be other pieces of data already in the store, and when you add that one piece of data, you satisfy that match. So then you'll get back all of the data, and you can run that continuation. So there's a persist flag. On the produce side, it probably isn't so obvious how you might use this, but on the consume side, what we'll show in a second, it's actually really critical for actually storing smart contracts in the store. So, all right. If you're lost a little bit, I would expect you to be at this point, but yeah.
And what if something bad happens? The disk goes bad or whatever?
So there's a range of things like that that are probably going to be exceptions thrown by LMDB. And we just basically bubble those up. You'll get the exception. We are not catching exceptions in any explicit way yet. I haven't seen so many of those so far, but obviously, if you're getting things like that, we want to know what they are in their sort of pure, unadulterated form. So we can't necessarily anticipate all the different exceptions that people would get. So that's why we're not recatching them and then turning them into our own error at this point. So, all right. On the other side, we have consume, and this is how you put continuations into the store. And again, we're searching the store, given all the patterns here, we're at the given channels, and we're trying to find a match for the data now, right? Instead of having a piece of data and trying to match that with a continuation in the store, we're now going in with a continuation and seeing if there's data that's in the store. And if no match is found, then we put the continuation into the store. We keep it in the store. But if a match is found, then we return this thing. And again, if a match is found, it doesn't actually stay in the store. You just get that continuation that you just handed back along with the data. So if you want to actually keep the continuation in the store, you have to set this persist flag to true. And that's essentially the mechanism that we use to store smart contracts. And I say that, and it may not really be apparent to anybody how this at all seems like a reasonable way of doing things. As you probably have seen, every read is a write, and every write is a read in some sense. Like we have these two verbs, and they don't really match up to our expectations of normally how a store may work. And part of that is because we're using this sort of old funky model, but really the primary motivation here is that we're trying to support the semantics of like the RowLang interpreter in terms of what it does. So when you think about, obviously some of you are familiar with the sort of hello world example. Boy, this Wi-Fi is slow. I know. And there it goes. It's dodgy Wi-Fi. All right, so like a for comprehension right here, like this part, like we're doing a consume here. Like we're storing a continuation when we do this kind of thing, right? This is using a little bit of syntactic sugar for the contract. But when we use something like this, or in the one with the bang syntax where you do a send, let me pull up another version of that. Oh,
Old syntax. Isn't that wonderful? We discovered that.
is this on master?
If you look in linking, you'll get
Linking has the new one? Yeah.
about
Oh, this is Michael Birch's stuff. I'll show the standard out contract. Because I wrote that, and I know that it's got a bang in there. Right. So for example, when we're sending here, that's a produce. That maps to a produce in the store, right? And so obviously what's happening here is we're looking at the channel standard out. We're producing on that channel with these two pieces of data here, the actual string and then the acknowledgement channel here, right? And then this here, when this is reduced to normal form and plugged into our space here, this is consume with a produce inside of it. So there's a really direct mapping between these RowLang constructs and the produce and consume calls that you saw just back there. So that's why this looks kind of strange. This isn't a storage layer that supports just like persisting blocks in a Merkle tree yet. The thing that we've designed here as RSpace is really designed to support the RowLang execution environment. So does that make sense to people? Might be a good time to open it up for some intermediate questions before I get too further into this, so that if anybody has any. Yep. Mike.
Got it. Sometimes there's a dependency where there's a need for multiple reads dependent on one write, or there be multiple matches, and then the language throws out those that don't match, or multiple pending matches, and the language throws out the ones that didn't match. Does that make sense? It's a sum in the pi calculus.
Yeah, so you're saying that there's basically the non-determinism in terms of which one gets selected? Yeah.
And that there would be pending possible matches that need to be thrown away.
Yeah. So we kind of do
Base
in
construct.
the innards of, I was just working on this the other day, so. In the innards of, I will answer your question in just a moment, I apologize. want to give some context for myself and for the Scala developers who are here. So when we are doing a match, and we're finding match candidates, obviously one way we could do this is we could just start taking things directly out of the store and finding a match. But then the important part is that the things that aren't the match, we actually need to make sure they stay in the store. We can't just take them out and remove them in that regard. So essentially we do a sort of speculative matching where we put together a cache of all of the match candidates, and they're shuffled so that there's a non-deterministic choice. You go through this cache looking for potential match candidates speculatively, and when you find one that satisfies the entire match, then we return that, right? But if there's not, then obviously the store is intact and everything goes on as is. Does that answer your question? Yeah? Okay. Anything else? I mean, if you just don't understand period, it's also a good time to say that, so. Christian.
So what's the format of the actual tuples?
Yes, right. So, I mean, our representation, part of the reason we call it R space is not the RowLang tuple spaces. We don't really use tuples per se. You could think of them as 4 tuples of channel pattern or patterns. Well, do channel channel data, which would be like sequence of A, and then you would do like a nested 2-tuple of patterns per continuation. So I'll write on the whiteboard. That would make sense. So it'd be like channel, we'll do seek of A, and then there's like the subtuple here. This would be seek P, K. Yeah. Does that make sense? So this is the data, all the bits of data. And then for each continuation, there is a set of patterns for that continuation. And this is a channel, or this is actually a seek of channel, excuse me. So channels. When you're putting a piece of data in, this is always a singleton list in the way it gets stored, right? Singleton sequence. When you're putting patterns, when you're putting continuations in, this is, if you're going to have a join in RowLang syntax, you're going to have multiple channels. So that's why we have a seek here as well. That makes sense.
And what's a simple example of storing some contract that you run repeatedly or something?
A join is like you're asking what's an example?
No, I just mean
core.
Right.
Right.
So the interpreter turns that into a produce call.
How could I not know this? But that's because essentially I've designed the API of this library, so I don't have to know anything about the RowLang innards, and that was why. So it's the MacGuffin there. I mean, all of the real rubber hitting the road happens in their implementation of match. So Kyle wrote this really fancy matcher for RowLang, and because he supplied that to me as a type class instance, I don't really need to know all of the vagaries. I do know some of the vagaries of what goes on in there, but I
You
don't
wrote
need
the
to know.
type class instance.
That's right. I wrote the type class instance. So, yeah. All right. So, Christian, does that sort of satisfy? Okay. Martin?
is on. So the matching, is it simply looking for all of the names that are matching to the name that you're sending on?
The matcher is really cool, and maybe I'll go over it more on my presentation on Tuesday. But it is basically taking the spatial type checking algorithm with free variables in it and finding a when the spatial type check succeeds, we take all of the free variables that you used and we give the values that were present. So you can write RowLang patterns. You can basically write a RowLang term with a free variable in it, and it will capture whatever value is there. There's a little subtlety, and I'll explain that some other time.
It's like fully substituted. Like we don't pass the environment around in the innards of our space. Like he's just plugged that all in so that, you know, that part is taken care of.
Okay, so it looks at a name, which is a quoted process, and that process might have some free variables in it, and then you substitute or try to make those free variables so that it matches a more general representation of that process? Or?
So you can match arbitrary RowLang terms and capture pieces of them. It's really kind of cool.
Don't have any good running examples to show you of that right now, but he's your man, so. Okay. Still, if anybody has any, like, you know, if I don't understand, help me understand questions too. I'm happy to field those, but if not, we can just sort of continue having a gander. Okay, cool. So yeah, I mean, core implementation comes to all of about 300 lines of code, 330 lines of code at this point. This is what sort of like the main semantics are. There's like another class that is like the underlying put and get things and remove things from LMDB. Didn't mention that before, but we use LMDB, the Lightning Memory Mapped database. Sort of came out of the Open LDAP project. This uses B+ trees. It's like compares pretty favorably to common choices like LevelDB, Kyoto Cabinet, Berkeley DB, classic sort of key value stores. The fact that it's memory mapped is really cool. So essentially, you know, they like page out virtual memory, and when you write to that memory, it, you know, puts it on disk for you. So it's pretty efficient in that regard. It's getting a little bit of uptake in the blockchain space too. In fact, the LMDB developer is working on the Monero project, so I would expect that you'll see it in more and more projects as time goes on. So yeah, I mean, I don't know if people are, there's not that many Scala developers here. I don't know if people are really super interested in going through line by line and looking at the code, but essentially like the idea here, and when we're producing, we're gonna go and look for a produce candidate. And if we find a produce candidate, we get back this produce candidate, then we are going to remove the waiting continuation from the store. Produce candidate is a continuation. So we're gonna remove this waiting continuation from the store. We're gonna go through all of those data candidates and we're gonna remove them from the store as well. And then we're gonna give you both of those things back. Similar idea here, if there's nothing in the store, then we're gonna store that piece of data in the store as well. And then
Are you getting to your sort of,
Are you headed toward things, architectural decisions you need to make, or is this pretty much all solid? Because that's the impression I'm getting, is that there aren't very many questions.
there are some future things moving, yeah. So like, for example, we have to support history and rollback, and we've started talking about that in like the last week, for example. So this is like to support Casper. And so I can shed some light on that as well. But I was just going to sort of talk about sort of as it exists today, what it looks like. So, consuming, similar idea here. We go and we look for data candidates and pieces of data that match, as we talked about before. And if we don't find any, then we store that continuation. But if we find some candidates, then we hand them back to you. So that's the general gist of that. So recently we've added system processes. And they don't really, they're part RowLang interpreter, part Tuple Space at this point. But the idea here is that if we want to write effectful code in what we call system contracts, so not blockchain contracts, but the contracts that run below that, you want to maybe do things like write to standard out, standard error. Now, eventually, we're sort of intending to use object capabilities, but for now, we just have these public names. And so you can send a message to standard out ACK. I'll use the other version of this that's just standard out so you can get the basic idea. But pretty simple. You have this name standard out. It's in the tuple space when you bring up the tuple space. You can write to it, and it's going to print out whatever it finds. Currently, we haven't wired it up to the pretty printer, so what you're going to see is like an AST representation of that string. But eventually, this mechanism will be combined with sort of the object capability disciplines so that these will be private names. And only the system contracts will be granted reference to these private names. And they will be able to do things like communicate over the network, do a UDP server, do a TCP server. So if you wanted to write an HTTP server in RowLang that ran as a system contract, you would be able to do that. And blockchain contracts would be able to be granted access to that thing with the object capability reference, but they wouldn't just be there necessarily as public names like this. Right now, we just have them as public names. They have ambient authority, as we say, with object capabilities, but in the future that will change. So standard out is pretty simple. We also have a version that after printing to standard out sends an acknowledgement message as well. That was the one I just showed. Here it is again. So basic idea is that like the tuple space can also be seen as this place where this hub of communication between RowLang and the network and bits of the outside world. That things like our communications layer via Casper will be talking, in the initial implementation at least, we'll be talking to the tuple space using produces and consumes, and then the rollback functions as well. And then there's also, if you want to extend the code, there are these static system processes where there are Scala implementations of these. And we don't actually store real Scala continuations in the store because it's kind of unnecessary. We essentially have like a lookup table where we know at that name there is a bit of Scala code that we can run. So we've written a mapping between those two things. You can run that Scala code, so we have the Scala code that writes standard out. We call that a static system process in the sense that it's kind of hard-coded. We're also working on an FFI, and we call that a dynamic system process. The initial version of that would be like you could load a JVM library, a Java library, a Scala library, and that you would be able to make method calls using hopefully some nice syntactic sugar that's on its way to make this a lot easier so you're not sending and receiving using strings and things. But we will have a way of basically being able to load in libraries from the outside world and access them through the FFI. This is especially important for cryptography where we don't necessarily want to be the ones shipping that along with the node. we want to be able for, because there are export restrictions on that kind of thing. So it's like, I think so, yeah. So we want to be able to have that part shipped separately. Yeah, so. Okay, I don't have much more to say at this point, but I'd be glad to open it up for more questions. Anyone?
So at some point, we'd like to support the idea of broadcasting, that you send on a pattern rather than sending on a name. How much work would that be to alter the current design to do that?
Yeah, I mean, non-trivial, but, couple sprints maybe.
I mean, can you encapsulate that in the matcher? Is that something that, or is it doing a literal match on the names at the moment? I'm not asking you to do this before Mercury, just to be clear. This is definitely Venus.
I'm going to defer to Kyle on this one. I think he's got an answer.
So the matcher only fires up when you have when you found the same channel. So the matcher is not involved in the channel match is basically a bit match at the moment.
Right.
So we have they're RowLang terms, but we came up with a way to normalize them so that all of the structural equivalents fall out and you can do a bit compare.
One other thing I just wanted to point out was, as you said, the format of the continuation is completely irrelevant to you. So this is a really useful library. Any language could use this and store their language's continuation in there and pull it out.
Yeah. One of the, so like in some of the examples that we packaged up with the library, I'll show you. So we did this sort of like address book examples, sort of trivial thing I threw together. It's the kind of thing you often see in like database examples, right? So we have like a notion of an entry in an address book with someone's name and address, email, phone, et cetera. We made like a custom pattern type here. So you're matching against the person's last name, the city they live in, the state. These are all the different candidates for matches that you could write. That's sort of expressed as like a sum type in Scala. And in the example we used here, I wrote a pretty simple class. Reason for doing it a class is that I used Java serialization, which is notoriously hairy. Greg has had terrible experience with it, but I'm sort of trolling Greg a little bit with this example. But the idea here is that this also implements function 1. So entries are our data type. And all we're doing is we're taking these entries and we're printing them out in sort of a nice format. So this is just like essentially an example of what a continuation could be. And generally, the model supports things that have no return type pretty well. I mean, things that return unit, I should say. You can imagine doing more complicated things where potentially you'd have one, but you run that continuation asynchronously in the RowLang interpreter and what they're doing, or in this case, we just run this and it does the effect for us. So yeah, that's like one example of one. Another one that I wrote for the sake of like testing this was what I call a captor, and it has a little mutable list buffer. This is where it starts to get really hairy, obviously, because when you're serializing and deserializing things that have mutable state, bad things happen sometimes. But essentially by marking it transient, we're not actually serializing the contents of this thing. We're just putting it in opaquely. And then what it's doing is when we pull it back out of the store, then we are taking all of these entries and we're putting them into the list buffer. So when it goes into the store, there's actually no contents of that thing. and it's not serializing with the contents of that thing. So all this is doing is every time you run this, it's adding the entries that you get into this list buffer. So this is like a way we can basically run this continuation, capture the results, and then inspect the results. You can see here I have this sort of getter here where I do res2 list. Hashcode and equals end up being necessary to implement ourselves here because of the vagaries of Java serialization as well. We don't want these things to, we want these things to essentially not use the default ones that come with Scala because there are dark corners if you do that as well. So moral of the story, I did this, don't do what I did. And I talked about this when I presented for the community. There are lots of great ways of serializing things. Java serialization, not one of them. We're using protocol buffers. It's like a pretty reasonable choice for this kind of thing. There are some Scala libraries for doing pickling that would also suit the purpose quite well. You could use JSON. That works too. You just take your JSON strings and turn them into bytes and put them in. So nothing's stopping you from doing that. Ah, yes. I wondered when somebody would ask.
The question was about threading.
Right now, we are leaning on the LMDB multi-version concurrency control. So whenever we start one of those produces and consumes, we open a transaction. This basically allowed us to get to releasing a library in under 2 months. We're working on a finer grained locking story for the next, by Mercury, I'll make that claim. Yeah. We're working on a finer grained locking mechanism. A lot of this stuff is going to change as we start to add ability to recall state as well. So that's going to be kind of intrinsically tied to some of the locking story as well. But right now, so if you look at the LMDB locking story, I believe it's basically got like a single writer. And so when you hold open a write transaction, the other guys, can't clobber that. And so that's how we deal with that question for now. But there will still be more to come on that. So. Anything else? All right.
So what?
How does it work? If it ends up being
Oh, hey.
All right, ladies and gentlemen, let's go ahead and get started. Please, if you could take your seats if you're milling around. All right, we're going to welcome Keith and Tim, who are going to speak on the virtual machine.
Okay. Am I live? Cool. Let's get started. My name's Keith McQueen. I've been with Pyrofex since early December. Before that, I didn't know what RChain was, and I didn't know what a blockchain was, and so I've been learning lots since then. I'm co-presenting with Tim Schäuble. Trying to get that right. We've been working in the Rosette virtual machine. The Rosette virtual machine was originally created by Greg and some others back in the early 1990s. It's a rather interestingly engineered piece of software. It does a lot of things. Primarily, it is a compiler for the RBL language mentioned by Henry, the Rosette base language. And Greg's here to keep us honest. Welcome, Greg.
Yeah, I'm sorry I missed Henry's talk. I was being interviewed and I feel bad about that.
It's okay. So Rosette is a combination of a compiler and a virtual machine. It compiles the Rosette base language, RBL, down into byte codes. And then it executes those byte codes in the virtual machine portion of Rosette. Was something else you wanted me to say?
I think that was it.
Okay, that was it. Okay, let's dive in. Okay, Rosette is an actor uses an actor model. There are actors and objects within the system. So it starts out with an object called a context. A context it contains a piece of code, it contains the data, it contains where the result of executing that piece of code is going to end up. It contains the arguments to the piece of code, and so it's kind of the basic piece that goes into the virtual machine. There is a thing called a strand pool. It's basically a queue of objects that are, or contexts that are ready to be executed. They have everything they need. They're ready to go, and so that when that context time comes up, it's ready to go. It gets executed. A context can have children, so that there's a concept of nesting of these context objects. And each child context has a reference to its parent, so that when it is done executing, it can pass the data back up the line to its parent, so its parent can then be ready to execute. Let's see. And assuming that a given context, a given parent context has received all of the data that it needs to execute, then it may be ready to execute. So it may be scheduled. And so that happens when there are no outstanding, no unfinished business for that context. This is kind of what the internals of a context looks like. We have the program counter within the context piece of code, not the overall system, just within its own piece of code. We have an outstanding, and forgive me, I don't recall exactly.
It tells us how many
arguments are left?
How many are left unfinished? Okay. We have a result and a target, the arguments, and then a pointer to the code, and a pointer to any parent context that this context may have. Starts out by installing a context that just basically creates it and gets it ready to go in the system. Now, if we dive into RBL, we have an example here that we've created to show how this system works. We're defining an operation. We're defining an actor. And then within that actor, we're defining a method called return one, and it does something incredibly complex. It returns one, as you might have guessed. And then we're creating an instance of that actor and calling it foo. Go ahead, Mike.
There you're defining an operation with the name return one and a method with the same name. Is that required, or is that just common practice, or what?
Greg says yes. We puzzled over that, Tim and I, but Greg says yes.
So think of the operation as like a key. So think of the operation as like a key, and that key together with the arguments go into the mailbox of the target, which is the actor where you're invoking where you wish to invoke the method, right? So that message arrives in the mailbox, and then at some point, the actor's at a place where it pulls that message off of the mailbox queue, and now it says, okay, the key is return one. Do I have any method code that is associated with that key? So it goes down its list of methods. Here's one called return one, and then it invokes it.
Define multiple actors that use that same key? Or
Yeah,
are they
and that's how you
scoped?
get polymorphism, right? That's the actor style, the actor version. So think of the operation as if you're familiar with Common Lisp, that's a generic function, and that's a multi-method. Yeah.
Okay. So we're going to start out by how an actor gets invoked. We're going to start with a simple example. We're going to call return one with a parameter of foo, and it returns one. Okay. Now we're going to step it up a notch. We now have two contexts. We have this inner one, which calls return one. And then we have an outer one, which calls the addition primitive with a parameter of 1 and whatever it would have been, whatever will be returned from this inner context. Does that make sense to everybody? Let's see. And of course, I got ahead of myself. Okay, and the end result we're hoping is 2, because we get 1 from return 1, we get 1 from this argument, and then we add the 2 together. This is where Tim's going to take it and dive deeper. Yes, you can get the mic.
Thank you. Okay, so now that we know some of the basics, we can look at what our example compiles down to, and it compiles down to this bytecode. And I'm going to walk you through the bytecode now. So log2 just creates an argument tuple which can hold 2 objects, and as you might have guessed, we need that to hold the 2 integers we want to add together. In the second step, we just put 1 into the
first position of the argument tuple. Third step, here you have to know what the global environment is in the Rosette VM. It's basically just a store that can store all kind of objects, and here we just put a reference from the plus operation into the target register. I think it's called target register because everything in Rosette is an actor, and you send messages to an actor/target. That's where the name is coming from. Now things start to get interesting. Outstanding 12.1. What this does, for the install context, it sets the PC field, the program counter, to 12, and it sets the outstanding field to 1. And right now we don't understand why yet. I will come back to that. Push alloc1. What this does, it creates a new context and installs it into the VM. Has an argument tuple for one object. And important to note here is that it has a reference to the initial context, which is the parent context. So we just, in the previous step, created a new context, which got installed, and this new context basically represents the return one invocation. Here, pretty simple, we put a reference to the foo instance into the first argument tuple of the newly created context. Same here with return one into the target register. And now what the XMIT opcode does, in general, it dispatches the arguments to the target. The next here means that after the dispatching, we will return control back to the VM. That means that the VM then will go back to the strand pool and get the next context. The arg1 here means that the result of the dispatch will be written into the arg1, which is the second argument position tuple, write that back into the parent context, because that's where we want to have it. What also happens here is that we schedule another context which contains the bytecode of the return one method, which, as we remember, just returns 1. So in the dispatch, when we do the dispatch, at some point we will call this method. This, by the way, is how 20-year-old C++ code looks like. The important things here are that we here install, we got our initial context, and here we override the initial context, not the initial context, the second context we created. We get that here and override it here with the bytecode of the return one method. And we also set the program counter to 0. And here we schedule that context. So it gets appended to the strand pool. That means at some point this context will be run by the VM. And what then gets run is this. Let's ignore the first opcode, extend 1. It's not important for our example here. At the second position, you can see that we just put 1 into the result register and then call this opcode, the return opcode. What this does, it just returns whatever is in the result register to its parent context. And we set the parent context earlier to the initial context. Then what return next also does is it schedules the parent context. And the next tells us again, or tells the VM again, that it should hand back control to the VM. Okay. So I just said that return next schedules the parent context, but is that always the case? No, it's not always the case. Here it was the case because the outstanding field of the parent context was set to 1 earlier. Now you can understand the outstanding opcode. Yeah, so the outstanding field, which gets set by the outstanding opcode, tells us how many arguments are missing in the parent context. Okay, so we just schedule the initial context again. At some point, the initial context will be picked up again by the VM and will run. And it will run at this position, at the 12th position. This is also why we had the 12 here, because we set PC to 12 there for the initial context. So we end there now. Yeah, that's basically what I just said. And then the dispatch function at position 12 will just perform the addition and gives up control to the VM. Yeah, that's it. Any questions?
Why'd you have to set the outstanding to 12? What was that number?
So there are two things. So there are two things there, right? One is the number of outstanding and where you're going to pick up control again.
Right.
Yeah, so the 12 is where you're going to pick up. Like it knows ahead of time, because it knows the layout of the bytecode, where to pick up the next instruction. That's what the PC is doing, is the next instruction.
Could be any value?
Could have been wherever that landed. It could have been. Yeah, exactly.
Exactly.
Yeah.
Oh, it's telling you what line to look for.
Yeah.
Okay, sorry.
Yeah.
Thanks.
It may be slightly confusing here as far as the arguments. You can see that in this code segment, there's arg0 is referenced twice. Those are two different arg0s. The first one is the arg0 of one context, and the second one is the arg0 of the inner context, the child context. Yeah. Yeah. Just wanted to make that clear.
Thank you. The plus gets invoked by XMIT?
By the last XMIT at position 12, yeah.
Or the dispatch that's
Yeah. Kyle?
On line 11, what is the arg1 next to the XMIT next?
It tells us, or tells the VM, where to write the result to in the parent context.
Okay, so where does it write the result for line 12 then?
Sorry?
Line 12 has an XMIT next. Where does it store its result?
It doesn't pass a result back in this case. That's why there's no
So it's thrown
target.
away?
Huh?
Yeah.
In this case, yes.
The circular file.
Right, because that's the top-level expression, that it is essentially
Exactly.
the REPL is the thing that gets it.
Cool.
Just one comment here. The virtual machine itself because we need to know about all of the RowLang code in order to do matching once something is transmitted, the compiled code is going to be used as a just-in-time, I'm sorry, the compiler here that outputs opcodes. The opcodes will be used in context where we're doing just-in-time compilation. And Kyle, I think you can say more about that.
So when you compile a RowLang term, you can actually tell which parts will be data and which parts will be code. And we never turn the parts that will be code back into data. So you can compile it down, not just in time, but you can compile it down. But you're still going to have RowLang that's uncompiled in there. And if you try and, there are specific syntactical constructs, and if you want, I can draw them on the board, where we evaluate things that were previously data. And at that point, you would have to just-in-time compile it. This one should be obvious. We have the ability to take a name and turn it back into a process and evaluate it. Hold on. This is very similar, except that we're doing the unquote on receive in the pattern. Similarly, if you use the nth method, you can pull a process out of a list. Lists have no side effects by themselves, but if the element here is a process with side effects, unwrapping it causes that RowLang process to be actually evaluated. If you are familiar with interpreters, you can actually look through the interpreter and you can figure out, oh, when are the things that we're doing that where we actually evaluate something.
Now a good time to tell the story, the C++ to Scala story, and does RBL stay forever or disappear? Or?
I'm not writing that story.
Mike, you want to talk about that?
So RBL is, as we mentioned, an optimization that we're going to be using. The RBL code right now is in the process of being translated. I'm sorry, the Rosette C++ code is in the process of being translated from 30-year-old C++ with all kinds of amazingly twitch-inducing optimizations, things like taking a pointer, and then because you know everything is aligned on the 4-byte word boundary, hey, we've got 2 free bits, let's stick tag information in there. So it's not actually a pointer anymore, right? All these things that people thought were cool 30 years ago and amazing. And
they were cool.
So,
it was shoehorn what you got to do into.
Of course, yes. Who needs more than 640K, right?
Exactly.
So then there's not only that, but then there's the fact that it was all written as mutable state. And our task was to translate it into Scala where everything is purely functional. So Tim has done some amazing monadic things. I mean, consider this. Anywhere in the code, you can get a pointer to an object. But a pointer to an object is just a reference into this big block of memory. If you want to be passing state around, you either just need to make a big block of memory that you're passing around through all the code, or you need to, we started out by having a VM state object with fields and so forth. So at this point, then you have to be passing that around and turn the pointers into paths through this object so that you can update the entire state thing. Had we known how complicated this would have been, we would have pushed back a lot harder on Greg for doing this style of translation. I cannot give enough kudos to the VM team for the work that they have been doing on this translation effort. That said, this VM was always intended as a stopgap measure for something that had the right semantics for the concurrency story. In the future, we intend to develop a machine that is specifically tailored to RowLang, optimize the heck out of that, transition over to using that for compiled bytecode. So eventually it will go away. In the meantime, RowScala, as it stands, does not include the RBL compiler. So we're looking at the potential to split off the RBL compiler component, keep that in C++, and use the Scala implementation of Rosette. We're trying to do this as modularly as possible, trying to take chunks as they come. The RBL compiler is a significant component that would take a long time to do, so we're trying to get as much of this into the project as possible without pushing the deadlines back. So we still have the end of the year goal of getting this delivered. Did that answer your question? Sorry, Dan?
I think so. I guess a little bit more. So does the RBL compiler do any kind of modern stuff like constant folding and stuff like this that would make it much better than an interpreter?
Yeah, I mean, there were a few tricks, right? The biggest trick is this context shredding idea, right? That was the main thing. It's like, so you have a lot of declarative information within Rosette about what's in sequence and what's in parallel, and so shredding the Rosette code down into a bunch of contexts is what it's really good at, and that's sort of that's the abstraction that we want. That's the special sauce that we want as a kind of layer in front of the hardware architecture for now, right? Because there isn't any other abstraction out there that has been pounded on as much in a commercial setting that has the concurrency piece at this level, right? This abstraction of concurrency in front of the hardware, right? If you try to, like LLVM is the most natural thing to go for, but their concurrency story is just all wrong. And it's there we go.
So the shredded contexts, each one of those is a bit of serial code, right?
Yeah, that's right. So it's basically what the compiler does is it shreds the Rosette code down into little strands of code with dependencies amongst them. Like you saw the whole dependency management thing with the outstanding and all of that. So that's what it's doing, is chopping up the code into little bitty tiny strands and then organizing them in terms of their dependencies.
And then there's this queue of contexts, and can you pick those off and run them in parallel? Where does the parallel?
Yeah, that's the idea. Is that you should. There are some caveats and gotchas in terms of our current implementation, but the whole idea of scheduling strands is that you should be able to pass them off to a thread in a thread pool.
Okay.
Yeah, that's the idea.
Is Graal interesting? Any of that stuff?
I don't know.
Oh, okay. It's a dynamic language VM stuff that the JVM folks are working on. So I've got a nod over here.
Yeah, I don't know enough about the project to be able to say it is interesting. That's all I really have to say.
I mean, The issue is like the JVM itself is just this giant beast, right? And we want to be a lot leaner and meaner, and get out to. I mean, wouldn't it be awesome if we had RowLang running in a toaster, right? That would be, or on a watch. Yeah, exactly. So I think this would be really nice, and so we want to be as lean and mean as possible. Also, you know, the JVM's idea of concurrency is very heavyweight, right? Which is why people write these green thread libraries on top of the JVM for exactly that reason, right? So maybe we could just cut out all of that stuff and get closer to the metal. That's the hope, anyway.
Okay.
At the moment, we're not making full use of the concurrency that the that Rosette provides. Most of the asynchrony and concurrency that we're actually making use of at the moment is all tied up in the tuple space, the dispatch and the retrieval and all that sort of stuff. But we have plans for Venus on how to extend this and make more fundamental use of it.
Okay, that doesn't come through very much in the architecture. Well, maybe it does in the architecture document a little bit. But to say that the JVM is heavyweight and we want to get past it, and then to write all the code in Scala makes my head tilt a little bit.
Yeah, that's because. So the implementation is iterative, right? So we want to self-host. So once we get a working version, then we're gonna self-host and implement RowLang, the compiler, everything else in RowLang.
Okay.
Yeah. So then kick away the.
So we have native code generation.
Yeah, that's the idea.
Who's running the RowLang compiler and running? I haven't started that one yet.
What's that?
The RowLang compiler in RowLang?
Yeah, that's the idea. Everything, we should self-host. So we rewrite the whole thing in RowLang.
Any more questions? Cool. Thank you.
Huh? We're a little ahead of schedule. Oh, 15? 15. Okay, let's take a break. We're a little ahead of schedule, so we'll take a 30-minute break. Be back here at 11 o'clock, right? Yeah. Be back here at 11 for more fun and games.